Hi everyone and welcome back to my channel. So today I will discuss the transformers algorithm, which is came from the Attention's its own unique papers. The reason I discuss this algorithm because this is the foundation knowledge for LLM, VLM, or the latest AI models. So now let's delve into it. So here is the outline of transformers. First of all, we will discuss about motivation and the context and why the transformer was created. The evolution of the deep learning sequence paradigm. So before we have transformers, the dominant sequential model were RNN, LSTM, GRU, or sequence to sequence. And sequence to sequence is the engine of the Google Translate back then, and it is research by Dr. Lê Quốc, one of the computer scientists from Vietnam, and it is processing sequential manners, but it have two major problems. The first is vanishing gradient. So basically, the model will forget information if the context is increased. And the next one is limited in parallel. So because of the sequential natures, it is extremely low in training. And then transformers propose and solve both two major problems by using the scale dot product attention, which is remove the recurrency, and solving for the vanishing gradient. The next one is use multi-head attentions, which support for the parallel in GPU, and we will discuss later. Now we move to the high-level architectures. So original transformers model was built as the engine for a translation task. And here's, as you can see, this is the OG architectures of it. So we need to be set a clear boundary and do not set ourselves the confusions because this is the original architectures. But the current latest AI model like LLM or VLM, it is use the architectures as decoders only. And we will discuss this later. So here's the image. The transformers original has two parts. Here is the encoders, and on the right side is the decoders. So here's the flow. For example, in the context of translations, first you have a raw sentence, you input to the encoders, and it's passed to the multi-head attentions. Here is where is used the attention mechanism, and then it's passing through. You can see here is have the two arrow. This is where it's passed for the K and V. Meanwhile, on the encoders, it has the mask multi-head attention, which means used to predict and generate. It is used to prevent for the model for the auto regression by predict something out of scope. And then it's also using the attention mechanism. However, here you can see it has one arrow here, it's passing for Q. And here at the multi-head attention, this one is the cross attention. And this is actually where it will use to translate and predict one. And here's the basic flow. First one is going to be past the raw sentences, and then it's going to be token ID, embedding, and on the papers, they use the 512 dimension, and also for 6 plot for both encoders and decoders. And after this, the X is the metric, is will pass for the positional encoding here, and surpass through the block, and then is going to be output for the probability. So encoders in the basic term is will receive the X and then create the key and value. Meanwhile, the decoders will respond to request by Q. So here is the cross attentions is where it's used to predict. Be aware that I still want to emphasize this is the original architectures. So you might be confused between the current LM or the decoders architectures. Now we move to the positional encoding. But what is it? So now we're coming back to the architectures. It's located here after we embedding the input. So the positional encoding is added each token embedding to provide the position information for it. So where the pose is the position here of the token and the I is the dimensional index. And the result vectors is added directly to the token embedding. So the model will receive for both the meaning and the position of the single vectors. So here is the math equations from the original papers and it has two versions. The first is the sine and the second one is cosine. But in the original papers, they decided to choose the sine version one. So in basic term, why we have to use the positional encoding? For example, you have a sentence like I love you. If you do not use the positional encoding, the model might be treated, for example, like you, I, love is the same thing. So we need to use the positional encoding because of it. It's play for the positions for each token to process for the sequential task. And here is the image that show more clearer view of the transformers architectures. So like what I mentioned before, here and here is the key and V from the encoders, while here is only Q from the encoders, and it's here for cross attention to predict and translate the word. So inside of this multi-head attentions, so here's is the architectures. What is multi-head attention? So basically that means like it's gonna be have many head of the model. I will discuss this later. And inside each head is going to be have the scale dot product attentions, which mean the self attention mechanism, the foundations of the transformers model here. And we will discuss this later. Now we move to the scale dot product attentions. So here is the foundation and one of the most important mechanism of the transformers. So self-attentions is a core mechanism that allow every token to look at every other token and decide how much to pay attention to it. And it's located in both encoders and decoders. So we have three types of attentions. The first one is self-attention. Next one is cross attentions and mask attentions. So I will coming back to the architectures one more. And here is the cross attention. And here is the mask attentions. And, uh, and attention here is the self-attentions. So we have three main vectors. The first is Q is query, which is the question to querying the predictions. The key is the key, represent for each token label descriptions, and V is value, the actual contents of each token contribute to the output. And here is the math equations from the papers. So in order to create the three these vectors, is need to have the input X we mentioned before. It is the embedding value, and then is will multiply with the weight metrics. And here is the way that is learnable from the models. So here is the image of visualization. How's it work? For example, here's the X metric or the vectors. It passing through the weight metric and then is will created the vectors here. And I reference from the website, what is transformers from IBM. And here is the most important thing and the crucial thing of the transformers architectures, that is the attentions. So this is the attentions mechanism. So it will have the input for key, Q, and value. And here's, I will explain inside of it. So first is we'll compute the Q and V by using the dot product operations here. And the T here is the transpose metric. I will discuss later. So if we compute the Q and V, we need to be scaled because if not, it's gonna be exploded the value. So we decided to scale for the d of key. That means like the dimension of key. So here's the thing. So we will ask the question, why we not scale for the dimension of Q or V? Actually, we can, because on the papers, they will set for the dimension for each one will be 64. And the reason why is use 64, we will discuss in the multi-head attentions later. But here we can understand that is we will use the dimension for 64. And then after this is we're using the software to convert the raw score into the probability between 0 and 1. And after this is we'll multiply with the V in order to having the attention score. And here's the visualizations. Like what I mentioned before, so since the Q and key is the metric, for instance, I will set for the metric for 18 and 16. So in order for both of the metric to calculate to each others, there's the metric. They need to be transposed here, which means 16 to 18. And then the result will be 18 and 18. So here is how it calculated. And and here you can see this is one of the problem of the original or the transformer, which is the quadratic in scaling, which is complexities for L of powers of 2. Next, we will move to the multi-head attention, like what we mentioned before. So here is the scale dot product attention. But why it have to be used for multi-head? So, like the transformers purpose is solve the problem for parallel here. So instead of is we'll be pushing for the full 512 dimension space into just one head. So the transformer is split the attention into each parallel head. So that is the reason why previously I mentioned the dimension of it is 512. They will divide it to 8 into 64. That is the reason. So here is the um, equations, the math equations of the head attentions. So basically, instead of it just running all the 512 dimension space into just one head, they will split the attention into multi-head, and at the end, it will concat for the h number of head and multiply with the weight output. And here is the image for visualization of multi-head attentions. And I also reference from IBM. So here is we have the 8 head result, and at the end is will concat into one place like this, and then it will multiply with weight output, and we will receive the output here. After we discuss about the transformers model, now we move to the strength and limitations. So the transformers review the foundation paradigm shift for the sequence modeling by enable fully parallel in training across all the token and connect any two token in just all of one step. But transformers still have really big structures weaknesses. Although this one is the foundation and the breakthrough for the AI, but we still see there's have really big weakness. The first is quadratic complexities, like I mentioned you before. If the more we're going to be scaling up, for example, like the Q and V is going to be L powers of 2, the complexities of it. So it's going to be really heavy and consume a lot of resource in order to calculate it, and is making really impractical for processing very long sequential task. For example, like some tasks that related to DNA, fold, etc., or predictions might be is really impractical. And the next one is inference memory footprint. So the KV cache grow linearly, so the length of the sequence generated is will consume a really big GPU. And the next one is the sequential inference bottleneck. So wide training is really parallel across all the token at once. But we will see that the token generation during the inference is still remains strictly sequential. Note that here we are discussing the original transformers. So be aware of it. So now this is the further information. So the current LLM architectures until to 2026. So I take these two image and it is actually the decoders architectures, decoder only one, but it's just correct in the concept because on the real architectures, it might be more complex. So be aware that this one is just a concept of it. So basically, it's still just take for the token input, and then it's passing for here is the mass self-attentions. So the mass attention here is going to be playing both for processing the attentions, and it's also used for predictions. Yes, it's also used for predictions, and then it's going to be passing through many decoder blocks like this, and then we will receive the output. So basically, this is the conceptual ideas for the current LLM models or VLM for some latest AI model recently. So that is the foundational and the basic knowledge of transformers. And we have surpassed for encoders, decoders, and how they work to each others, and how the self-attentions work, and the multi-head attentions as well. And we also surpass for the further information, which will discuss a little bit about the architectures of the decoders only model, which is currently widely used by almost of the chat or the AI models. And that is the end of the video today. And thank you everyone for watching. See you next time. Goodbye.